Okay.
The broadcast is now starting. All attendees are in listen-only mode.
Okay, everybody, welcome to, gosh, what is this, number 5 or 6?
5.
5, okay. Wow, welcome to our biomimicry, our 5th biomimicry class. This is Mila, and I'm just going to turn it over to Marie in a second. Hope you guys are all having a good summer, and I know that this is a busy time for a lot of folks, and a lot of people are on vacation, so we just wanted to remind everybody that I was able to get all of the past and the current presentations posted on the Peaks to Prairies website on the webinars page. So if anyone on your team misses this call, then it will be posted probably by Monday. So just let them know that if you're in contact with them. And if there's any questions, go ahead and let me know any logistical questions. And other than that, I'm going to turn it over to Marie.
Well, welcome. Class number 5. We're almost through with the instructional part of our biomimicry workshop. So today I wanted to talk to you about the intent of the class. It's really, we're going to finalize the integrating biology into design process. Talk about a deeper understanding of life's principles and explain the circle chart, and talk to you a little bit about using a systems approach. I know in my homework I had included a topic of communicating biomimicry to other disciplines, but I've decided to include that in next month's webinar instead, because the using a systems approach really fits in right now with what we're doing. And we will go through 2 of the life's principles as examples. You've been given homework, and each of your team is going to be reviewing one of life's principles. So I'll give you some examples and do the 2 that have not been assigned. We'll do an update on the in-person session, see if there's any questions about August homework, and finish with questions and comments. So, eyesight. The fires in Colorado have really demonstrated the need to live within life's principles or accept some pretty serious results. This month, your Eyesight Exercise has you looking for examples of life's principles in action at your eyesight. Recently, we have seen some very destructive fires in the western states, and I would like you to think about is that how would a thoughtful review of life's principles during the design phase of the housing developments that were affected have resulted in a more resilient community. And I'll ask you now if anyone has an eyesight experience that they want to share with the class. Raise your hand and Mila will unmute you.
I will unmute you, but we need a hand to be raised first.
Yeah, maybe no one has an eyesight, but
seems like some Colorado folks would have an interesting story to tell us
about the fires.
Yeah.
Okay, well, we'll just continue. One of the case studies I wanted to talk to you about is this one. It's the value, really the value of an eyesight. There's an architect who had studied biomimicry through a biomimicry workshop, and he was asked to design a training center at a site in New Mexico. The developers stated that all the required environmental studies had been performed, and they were especially lucky because no human artifacts had been found at the site, so there would not be a need to do any archaeological digs or protect any ruins. And the architect thought about this and said, well, there may be a problem. Why would no humans ever live here? So he visited the site and discovered through an eyesight observation that there were signs of earthquake activity. The site was a natural fire channel for wildfires, and the site was also in the natural floodplain. So he recommended that the training facility be moved to another site. The developers did not want to waste the money they had put into the site, so they proceeded with construction. And during the construction phase, the site was hit with both a fire and a flood. The flood occurred while the developer's family was visiting the site, and although they were able to evacuate to safety, it was enough to halt the construction and the site was abandoned. So we can remember that humans who were in touch with nature had realized through their own eyesight experiences that this was not a good place for humans to live. And so we can remember that in the context of the current fires in Colorado as well. Another case study I wanted to share with you is this one about polycarbonate plastics. Plastics are carbon-based materials composed of one or more building blocks strung together into long chains called polymers. Conventionally, the building blocks, they're called monomers, were formed by distilling crude oil and cracking its large carbon molecules into small two-carbon molecules called ethylene. These small ethylene molecules are then used as the starting material to synthesize a variety of carbon-based monomers that are then polymerized into an array of commercial plastics, including polycarbonate plastics. Polycarbonate plastics have many uses in a wide range of commercial products, from water bottles to optical lenses and mechanical and medical devices. The conventional polycarbonate production process is energy and hazardous chemical intensive, requiring the suspected endocrine-disrupting chemicals BPA and phosgene, infamous for its history as a chemical weapon. Polysynthetic organisms have found a different, life-friendly route to producing a wide range of complex carbon based on polymeric compounds such as polysaccharides and proteins that they need for their structural support, food, defenses, reproduction, etc. Instead of using crude oil as food and fuel and fodder, photosynthesis taps the abundant influx of solar energy to drive a cyclic system that draws carbon from the abundant pool of atmospheric carbon dioxide. But in order to overcome carbon dioxide's resistance to sharing its carbon atoms with other molecules, nature devised the ribosome enzyme, whose reactive center is able to coax carbon dioxide into bonding with the carbon atoms of an organic molecule. This key step of the Calvin cycle produces a building block from which all other carbon-based compounds in photosynthetic organisms are produced. The ribosome enzyme, having lost its energy in the process, gets recharged by the solar energy producing side of photosynthesis and is ready to grab another carbon atom to feed into this natural chemical factory. Cornell University chemistry professor Mr. Coates, Dr. Coates, took inspiration from the ribosome enzyme in the Calvin cycle. The result is a mimic of ribosome's reaction center, which bonds carbon dioxide to a natural epizide, a limonene oxide, derived from limonene oil, the major compound found in oils of citric fruit peels. The production process occurs at rates relevant to industry, close to ambient temperatures and conditions, and in an aqueous medium, and the final product is biodegradable. In 1994, Professor Coates and his colleagues founded the company Novomer LLC, based in Ithaca, New York, and filed a patent for his polycarbonate production process. So what's being mimicked here is the photosynthetic plant's ability to use carbon dioxide as a carbon source for the manufacture of carbon-based compounds such as sugars, vitamins, proteins, etc. The type of mimicry is that it's mimicking the process of photosynthesis. And some polycarbonates are available through novomer.com, but at the moment they are not advertising hard plastic consumer products, but they're working on that. So another interesting application of biomimicry. So back to our process of integrating biology into design. The challenge teams are now in the creating phase of the biomimicry methodology. So we've biologized the questions. We're working with our teams and with Nestle to discover natural models and abstract the design principles. And we will be working on emulating these best models and finding our solution. So again, in abstracting, you need to distill the biological method and mechanism and translate them into design principles. And your homework last month, excuse me, was to practice abstracting the biological methods, mechanisms from scientific literature, asked nature, and personal observations for your team's design challenge. And we recognize that this is one of the most critical and one of the most difficult components. And I wondered if anyone had any questions or comments on the abstracting process. At the in-person session, Taryn Mead will also be able to check your abstracting based on the scientific literature that you bring to the in-person session and help you with that process in case you're not quite sure of it. Has anyone raised their hand?
Nobody, oh yeah, we have one hand raised that I'll call on in just a second, but I also wanted to say that I just found that I'm finding this step one of the most, something I can really wrap my brain around, and it's just sort of, you know, it was hugely helpful to have Nestle assist us, the water team, with coming up with some examples, but then it's been really fun to kind of dive into the biology of it all, so.
Oh, well, that's great. It's the part people want to do first, but you can see how really biologizing your question, identifying your function, and identifying the context that your project sits in are really important pre-steps to actually looking for the solution. So someone has a question?
Yeah, I'm going to call on John Brink. Okay, you there, John?
Yes, I am. Can you hear me?
Yes.
Good. I found it challenging when my question was whether how precise the process needs to be. I found that when I did the abstracting from the examples you gave, I was kind of close, but not always exactly on the mark. And so my question is there just one right answer on these things, or are there sort of multiple ways of saying it? And I guess kind of a follow-up to that also would be whether you'd like to take a look at some of the things that we did and give us feedback on ways that we could have done it better.
Okay. Well, those are both great questions, and the actual abstracting is the answers that I gave to the problems that the worksheet that I gave you were probably written more in language that I understood as an engineer, so that just keep that in mind. Certainly describing and abstracting that principle is a personal, as long as is a personal decision of how to word it, and it's your language that you use in your team. If it resonates really well with you and with the other people, the problem usually comes in abstracting is that we want to copy the biology, and people like myself who have studied engineering and may not be really familiar with biological terms, or designers or business people who probably have less connection with the biological world would not understand it. So as long as it's clear to you and to your team and doesn't contain a lot of biological language, I would say that it's a correct abstracting. And again, Taryn Mead will help look at what you have abstracted from the scientific literature and tell you if you've abstracted it correctly. That's what she's going to be doing in the in-person session. The second question, if you would like to share with me some of the examples where you've abstracted biological principles from the scientific literature, I'd be glad to take a look at it and provide some comments back. So just send me an email, and with one or two examples of the biological literature that you've used and what abstracting principle you've extracted from that. Does that help?
I was thinking more in terms of the abstracting we did from the cases you gave us in the homework. than I was for our project, but either one would be helpful.
Whichever answer that you would like me to look at, if I can compare the abstracted examples, the abstracted language that you came up based on the worksheet I gave you with the ones that I came up with, and see if I think they say basically the same thing. If you'd like me to do that, send me your homework sheet. And if you want me to look at a few examples from the literature that you've done, I'll help with that as well.
Great, thank you.
Oh, any other questions or comments on that step? Okay. Well, let's move on. So now let's look at how systems work. So if humans really succeed in reaching the goal of living within life's principles, we will increase our chance of survival on Earth. So it's a real reward to actually live within life's principles. For many biomimics, and also those people having just been introduced to biomimicry, the underlying attraction to biomimicry is not just the opportunity for novel solutions, but the underlying current of hope and the ideas of being proactive, taking a step towards the goal of fitting in on this planet. Believing in the importance and necessary of living within Earth's operating conditions and following life's principles represents a change in our basic assumption in many ways. And we call this a paradigm shift. A paradigm shift is a complete change in core values and belief systems that facilitates a new condition. And I can say that I underwent a paradigm shift through studying both biomimicry and permaculture. And I do view my actions and my decisions differently since learning about this new science. So in this case, the new condition is sustainable living on our planet. Under new conditions, our current unsustainable living and designing habits would be deemed unacceptable. It takes persistence and it requires the right placement and the right timing, but this mindset shift is not an impossible change. So we can think about it in terms of our agricultural system, is that only 80 years ago, all the agriculture in the whole world was organic. So we have, in 80 years, we have had a paradigm shift of how we grow food, and now we're hopefully entering another paradigm shift where we say, gee, that might not be the best way, and maybe we can go back and relearn how we can do it organically. In order to alter Homo sapiens' effect on the Earth, people do need to behave differently. In order to change behavior, people must first change their thinking. A different mindset is needed. With new values and attitudes, people will act differently. They'll make decisions in alignment with their new values. So a paradigm shift is about changing attitude, changing mindset, and changing people's basic assumptions. So the renowned systems thinker, Donella Meadows' essay, Places to Intervene in the System, lists and explains the importance and the effectiveness of the multiple leverage points in a system. And a leverage point is a place where you can, one small change works like a lever. It can create a larger change. And so I've included a link to this article in your homework, and it definitely is worth a read. So as you do read that, think about the system that you operate in and where the important places you can intervene, where the leverage points are. So what is a system? Well, the Earth is a huge system. Countries are systems, cities are systems, and neighborhoods are systems. Neighborhoods are also components within the larger system of a city. A system is a group of independent but interrelated elements comprising a unified whole. In order to change the way a system is working and flowing, you must first define and understand parts of the system. You define the system, naming the centerpiece and determining the elements or key pieces that affect or are affected by other pieces of the system. And in biomimicry training, we learned an effective way of drawing out systems so that we could communicate across many disciplines, because what I saw affecting the system as an engineer was incomplete. And when business people and designers and biologists also put their parts of that system, we could see how all of those different disciplines affected the system that I was working in. So you can make a system include as much or as little as you like, but realize the more detailed your system understanding becomes by finding all of the elements, ties, interconnectedness, and relationships, the more you can see the whole picture. And then you can increase your chances of being able to effectively adjust the system's variables. Systems can be very complicated. They can be layered, and things are usually parts of numerous systems. Likewise, due to the complexity, there are lots of places to intervene and create both intended and sometimes unintended consequences. And as humans, we tend to want to change the rules of the system, which, if you've read that article by Donnella Meadows, that's a lower leverage point. The highest leverage point in a system is changing the way people think about things, and that's what we're trying to do with biomimicry. So what role do life's principles play in changing a system? Each principle applied fully and fully adopted likely requires a shift in the current overall purpose and goal of the design. As you might imagine, combining all principles together, the adoption of life's principles represents a complete paradigm shift. By changing what is held valuable and to what we hold our decisions accountable, using frameworks like full cost accounting and triple bottom line, this mindset change does not have to be limited. Instead, it widens the path for creation of new solutions that were previously thought unacceptable or impossible. So what are life's principles? Life on Earth is made up of an ever-changing and incredibly complex network of interconnected, interdependent organisms. Some form of life has managed to sustain itself on Earth for the past 3.8 billion years through ice ages, tsunamis, volcanoes, and even asteroids. This means that life has survived 3.8 billion years of testing and 3.8 billion years of rigorous selection that has resulted in a 99.9% failure rate. Only 1/10 of 1% of species that have ever lived on Earth survive today. In other words, the species surviving today are the success stories. In trying to identify and emulate the strategies these successful creatures share, life's principles provide us with an important tool for strategic design. Life's principles are what biomimics use to both drive and evaluate the sustainability and appropriateness of our designs. So scientists have been working for centuries trying to identify how nature works, to really unlock the secrets of survival and to unravel life's mysteries. With so many scientific papers published, it may seem that every organism has a unique way of surviving and even thriving in its niche of the environment. Upon closer consideration, though, some really distinct patterns emerge. Many creatures have similarities. They may have comparable shape or move liquid using the same mechanism or have similar response to danger or employ the same chemical reactions. In biomimicry, these patterns are called deep principles. For example, not every organism employs capillary action using the physical properties of surface tension to control the movement of water, but plants and a few animals do move liquid in this manner. Because of its frequent appearance in nature, capillary action is considered a deep principle. Some principles, such as being locally attuned and responsive, are even more common across species than the deep principles and are found uniformly across almost all organisms. The Biomimicry Guild and the Biomimicry Institute, along with many partners, have studied, compiled, and distilled scientific research to create a collection of these more fundamental principles, now known in biomimicry as life's principles. Life's principles are intended to represent nature's strategy for sustainability, that is, how life has sustained on Earth for 3.8 billion years. So in one of the previous webinars, we talked about the seeds of biomimicry, and I wanted to see how they relate to life's principles. So the three seeds of biomimicry, ethos, reconnect, and emulate, represent the foundation of the biomimicry meme. Life's principles are a part of each seed. This overlap occurs because life's principles do play a vital role in the foundation of each seed. To someone new to biomimicry, life's principles can be the link or entry point into a seed they haven't yet explored. For those working in different realms, the set of life's principle is a tool for integrating the genius of nature into your work. Life's principles provide a high set of standards distilled from other creatures' successes to help redefine and guide our choices as we strive to fit in here on Earth. Life's principles are the basis for the mindset shift that must happen in order for sustainability to become ingrained in our ethos. In our Reconnect with Nature, life's principles provide a bridge to biology. It's like a Biology 101 shorthand course. These principles are the summary of things scientists have recognized in nature, and they are principles that biomimic can witness and develop as you explore nature. So hopefully you have seen some examples of life's principles in your eyesight exercises. While observing these principles, biomimics can experience the interconnectedness of the natural world, humans included. As people become reconnected to nature, it becomes more instinctual to see ourselves as being part of the Earth as a system, not independent from it. In emulation, life's principles provide tools for the different aspects of the biomimicry process. Life's principles can provide a visioning tool and help guide a project's priorities. During design, life's principles can be inspirational and provide a framework for choosing among design options. After a design is complete, life's principles can be the basis for continuing assessment on how the final outcome of the project performs. So distilling and capturing all these principles and patterns and their relationship as a single document called Life's Principles has itself been a very evolving process. Over the years, the principles have taken many forms, beginning as an unordered list in Janine Benio's book, Biomimicry, Innovation Inspired by Nature, then adding a suite of principles from the book, The Way Life Works by Holgrand, and then becoming an ordered list, and then a list with a hierarchy. A few years ago, a major restructuring evolved into a hierarchical drawing. Some of you have seen the butterfly, which then morphed into the current circle diagram. The Biomimicry Guild and the Biomimicry Institute continued to collect and respond to feedback to define life's principles. Over many months, they gathered feedback from practitioners and biologists to create the context and the diagram for the current list of life's principles. So this slide compares the list of life's principles that I learned in my 2YC program, the version 2.8, and the ones that are articulated by and the ones in the 2.8 version are the ones that are articulated in the Great Sand Dunes and the TRI case studies. And the version 2010 is the one we are working on in the class. So you can see in the green highlighted life's principles how some of them were still felt that they were valid life's principles, and some were added and some were changed to be more realistic based on further study and further input from biologists and other practitioners of biomimicry. So now let's look at the circle, and I wanted to explain the circle diagram to you. So I sent it to you in your homework, so hopefully many of you have it available to look at while we walk through it. Here it is if you don't have it in front of you. So the set of life's principles is an important tool, a standard for reference and for integrating biomimicry into your workplace and even your life as a whole. Life's principles can be the underlying ethos and aspirational goals for the scoping and visioning for a project, as well as provide a tangible list for which to evaluate a design. Given that life's principles are embedded into so many aspects of implementing biomimicry, we need to develop a deeper understanding of what each principle means and start to recognize these principles in nature. So these life's principles are presented as a one-page diagram with a set of definitions on the back. This diagram is designed so that the one page may stand alone. It was an extremely difficult task. It is rather daunting to sum up into one two-dimensional representation strategies of 30 million species that have evolved over 3.8 billion years. So the diagram contains several elements and is structured with specific intentions. The webinar will go into the details of two of life's principles, and your class assignment has each team presenting the remaining life principles next month. In addition, the adapter team will lead a class exercise during the in-person session that will take us further into the study of life's principles as they relate to the organisms that are found in the southwestern Rocky Mountains. In this diagram, you will find the title caption small circle in the upper left, which puts forth what life's principles are. So they're design lessons from nature. It's meant to complement the circularity of the principles themselves, reminding us that we must look at these as a whole set, and the absence of one creates an incomplete picture. So sometimes I use the list of life's principles to measure a project that I'm doing, and even though I may not include all of life's principles into the design of that project, I can see where there would be some potential problems down the road for the based on the life's principles that were not met during the design phase. The suite of principles is a result of and subject to the operating conditions of the planet, found in the blue arrow on the lower left side of the circle. Life's operating conditions remind us of what is driving these adaptations. The center of the circle is both the aspirational goal and the emergent properties of these principles, is that life creates conditions conducive to life. The principles are clustered in similarity and relatedness as well as with a degree of hierarchy. It's reasonable to ask the question, how does life achieve that principle? And find the answer in the principle that lies between the main principle and the circle in the center. Just as no principle stands alone, all principles are interconnected, and the case may be made for a rearrangement of the sub-principles and master principles, as we saw in the previous slide, the change between 2008 and 2010. Using the tool and the diagram as it suits you, keep in mind that it is the integration and organization of the collective and collaborative suite of principles that yields life its success. Biomimicry believe that it will do the same for humans. So life's principles, again, represents the overarching patterns found among species surviving and thriving here on Earth. Humans live and function within the same operating conditions as the other creatures living on Earth, so life's principles provide us with an important insight into what species around us are doing that contributes to their success. These overarching patterns provide inspirational and innovative strategies for survival, and they're also meant to view nature as a model. Life's principles also show how nature is our mentor. The principles provide aspirational ideals. Fitting in on Earth is more than just our own survival. Humans are also part of the larger system and can contribute to the overall health on the planet. Life's principles show how a seemingly isolated design is in fact linked to a larger and larger system and ultimately part of the largest system, the planet Earth. Life on Earth is interdependent. Life's principles illustrate how all species link as one interconnected system. So life's principles are sustainable benchmarks. There are designs to accomplish these principles. This is nature as measure. If these principles are used as the overarching pattern held in common by the surviving species on Earth, if designers purposely set out to fulfill these principles, our designs would likely fit in on Earth and facilitate the survival of our species and others over the long haul. To fit in on Earth, humans can strive to live and design in alignment with life's principles and measure our designs against them. Life integrates these principles into an optimal configuration to create conditions conducive to life. And it reminds us that they're all uniquely woven together into elegant solutions. The Life's Principles circle diagram, with the principles broken into categories, makes patterns visible, understandable, and useful. And Life's Principles as a diagram takes the complexity of how all of nature works and creates a tool consisting of manageable principles. While this dissection may permit application or emulation of just single principles, it is the inclusion of all of them that fosters a truly sustainable design, not just in our own work, but for life as well, and this is the true secret of their elegance and success. So the phrase, life creates conditions conducive to life, is at the center of the life circle. This concept is the goal and the reason for using life's principles as a tool. But what is life, and how does a designer create conditions to support life? An explicit definition of life is hard to find. Some definitions give lists of requirements like homeostasis, growth, metabolism, adaptation, reproduction, and growth, while others designate minimal requirements like responding to stimuli inside and outside of themselves or being part of a network or systems. Humans, ironically, tend to readily accept the first type of definition while tending to avoid the later. We don't think of ourselves as part of the system. We spend so much effort trying to overcome our surroundings rather than responding to them, and consistently work to eradicate ourselves from the natural systems around us. Of course, in reality, we fit all of these definitions, and therefore it behooves us to work towards creating conditions conducive to both ourselves and to love other living organisms. The requirement for life as described by scientist John Wald are liquid water, elements needed for metabolism and reproduction, an energy source, and a suitable environmental condition. How can humans bring these requirements to the forefront and evaluate how conducive to life our actions and designs are? We can do that by using life's principles as a way to gauge our success. If other life creates conditions conducive to life by successfully accomplishing all the categories of life's principles, humans can use life's principles as aspirational goals to aim towards, and by succeeding with life's principles, designers can survive and thrive as well as contribute to the survival of life on Earth. The foundation and need for the mindset shift to life's principles is Earth's operating conditions. This is because they are the non-negotiable characteristics of the planet. We remember their sunlight limits and boundaries, dynamic non-equilibrium, and sunlight, and cyclical processes. So life strategies have evolved to function well in the same context that human designs must, the context of the Earth. Life survives by working within and even leveraging the surrounding context within which the strategy must operate, including the context of the planet. Of course, humans live here on Earth, and our designs must function within this context as well. Of the many properties on Earth, some universal conditions have particularly large influence on Earth's occupancy, i.e. the people who live here or the organisms who live here. and we refer to these as life's operating conditions. They are identified and named because they are conditions that life is subjected to, either directly or indirectly, and therefore organisms must evolve strategies in response to them. While it is possible to identify random organisms that may have managed to completely avoid a specific operating condition, for example, there are bacteria that live in bedrock several kilometers beneath the soil surface and probably aren't aren't subject to direct sunlight. It's safe to say that 99.9% of all life does need to function well within these given operating conditions. Each of these operating conditions act at the global scale, but manifest themselves at the local scale. Both temporally and spatially, these conditions have a wide variation of effects on life and play relatively different roles depending on the local context. Yet independent of all this diversity, all of life must learn to operate within the conditions in order to survive. And this is the challenge that lies before us as a species as well. So let's look at the Earth's operating conditions. So sunlight is really electromagnetic radiation given off by the sun. Traveling 93 million miles to reach the Earth, it warms the planet to a temperature that can support life. This heat supports the metabolism of millions of species who are unable to warm themselves internally and helps out those who can. The variable heat as the planet moves from day to night, the season to season, drives the currents in the ocean, the weather, the climate, and the water cycle. These in turn dictate the strategies that life evolves as a means to adapt to the conditions it survives in. The photons arriving from the sun also provide light on a periodic basis, and sunlight is the primary source of energy for much of life on Earth. Plants, marine algae, and some bacteria, these are the primary producers, directly use the energy from the sunlight to fuel photosynthetic reactions that produce the building blocks needed for life. Every year, they convert over 100 billion tons of CO2 and hydrogen from water into sugars, yielding oxygen as their waste product. Those creatures not producing their own energy via photosynthesis still rely on sunlight indirectly for energy as they eat the primary producers, or the secondary producers eat the primary producers to gain needed energy. In this way, sunlight becomes highly influential as an operating condition of the planet. Water is just as important. 70% of the surface of the Earth is covered by water. Visually, it's easy to see the Earth as a water-based world, where water in all its forms, solid, liquid, and gas, coexist. Earth is water-based not only because of the sheer amount of water on the planet, but also because water itself has properties that make it special in its capacity for supporting life. As a solvent, water maintains a liquid state over a relatively large temperature range, largely due to its ability to undergo hydrogen bonding, weak bonds that play a key role throughout life's chemistry. Water's polarity facilitates the formation of membranes, critical components of cellular activity. Life's chemical transformations, such as photosynthesis, are directly or indirectly associated with water. For an individual, water is vital for its role as a solvent and its player in metabolic functions. Every organism alive today depends on water internally for its cellular processes. Yet, even externally, the presence or absence of water drives the emergence of a whole suite of strategies for life. Everything responds to water, from cypress trees with flooded roots, barnacles that seal up tight as the tide recedes, or the resurrection fern, whose dormancy can last for years until water returns. Water is clearly a key operating condition of Earth. And finally, life on Earth is also affected by the properties of gravity. Gravity or gravitation is the force of attraction between masses. The specific gravitational properties of the Earth, unlike other planets, have also been key to the success of life here. The most obvious example is the gravity keeping all species and artifacts firmly on the surface of the Earth. Gravity has a direct effect on individuals, as all of life on Earth requires enough structure to support against collapse under Earth's gravitational conditions. Life responds to gravity when flying, when orienting, when balancing, and movement. Life works against gravity when moving liquids, growing tall, or springing up. Life relies on gravity when staying put, when growing roots, and landing. Even the location of organs within the body depends on the body's orientation towards the Earth. Yet beyond these individual adaptations, a broad-scale gravity is responsible for the Earth's orbit around the Sun, Moon's orbit around the Earth, the formation of the tides, and natural convection, which drives both ocean and air currents. So this operating condition cannot be ignored. So life is subject to dynamic non-equilibrium, and conditions on Earth are constantly changing. This means they are dynamic. The conditions at any given time will never look, act, or be like any other point in time. These differences and the shifts from one state to another, however, are not moving towards a guaranteed expected state or equilibrium. The planet is not moving towards an ordered state. The tectonic plates are not moving towards unification or dissolution. Even ecosystems, while they undergo succession, such as a field tending to succeed to a forest, equilibrium is seldom reached, and if it is, it's merely for a blink in time. A fire comes, a disease passes through, or a flood washes away the soil. This example spans many years, but the same conditions apply to all other scales as well, even our own individual bodies. While we tend towards an aging body, many disturbances along the way determine how quickly we get there. As such, it makes it difficult to predict, let alone define, what strategies we must employ for our own functional well-being over the long haul. Astronauts, after seeing Earth set in the black background of space, often comment on how fragile the Earth looks with only a thin layer of atmosphere for protection. That pink ball on the right globe is all the atmosphere in our planet. The blue ball on the left is all the water on our planet. It's critical to remember that everything on Earth is finite. All resources, even solar energy, are limited. These limits exist due to the Earth's specific physical properties, including its location in the universe and the materials that formed the planet. These Earth-encompassing realities are the most influential of Earth's boundary conditions. They are basically the fundamental rules describing the way physics on Earth works. These laws include, but are not limited to, the law of gravity, conservation of mass and energy, conservation of movement, Newton's 3 laws of motion, and the laws of thermodynamics. While these limits and boundaries act at a global scale, they play out at many smaller scales. Ecosystems are often defined by the limits to which they are subjected. For example, the relative presence or absence of water, the minerals that are in the soil, or the above freezing degree days. Boundaries, inside and outside, play an important role in chemical reactions, in cellular functions, and in organisms' identities. Being subject to both, work within and leverage their effect. Like dynamic non-equilibrium, cyclical processes involve change. The critical difference, however, is that the Earth's many cyclical processes each hold a measure of predictability. The changing of the seasons, the cycle of day and night, the tides are all examples of cycles found on Earth. They have their own periodicity, which varies in context specific, but the predictability of the changes become an important operating condition in which life must thrive. These cycles may affect the resources available or add time-sensitive variables to the Earth as a context, but they are dependable, continuing the cycle time after time or location after location. So these cycles need to be accounted for. The creature or organism needs to be able to regulate its body temperature at night as well as during the day, for example. But the Earth's cycles are also an opportunity. Creatures live in a desert can leverage the different temperatures within the day-night cycle to manage their own temperature. The predictability of this operating condition has resulted in millions of unique and context-specific adaptations to the cycle, yet also result in one very common deep principle. Life has learned to take advantage of those cycles. As such, cyclical processes also shows up well within the circle as one of life's principles. This is because in addition to life being subject to cyclical processes, it also creates cyclical processes. Since it's surrounded by them, life has evolved to leverage these processes. They can be biotic or abiotic in origin. Everything from the cycles of the blood in the circulatory system to migratory cycles to monsoon seasons creates a context that life is subjected to both directly and indirectly. So biomimicry strives to emulate the general patterns and processes found in nature, and we refer to these general patterns and processes as life's principles. Life's principles outline strategies for thriving under the operating conditions on Earth, and they represent the sustainable system that we wish to emulate. As part of your homework, each team was assigned one of the main life's principles and the associated strategies to share with the class next month. We will learn about these from the teams next month, so this webinar will provide information on the remaining two main principles and provide an example of what is expected from your team. Just a note is that I have requested that you submit some of your homework on August 3rd, which includes the summary and the registration for the in-person session. The work on life's principles can be submitted just the day before the webinar, and I'll talk about that at the end of this webinar. So let's look at two of the life's principles that were not assigned and go into detail with them. So evolve to survive. The definition is continually incorporate and embody information to ensure an enduring performance. So evolution is change that spans across generations, traits that are passed on to the young. Genetic evolution arises through mutations in the code of individuals or from the recombination of genes during sexual reproduction. The process of natural selection shifts the beneficial and detrimental mutations, favoring individuals with beneficial ones. Since the trait is within their genetic code, which is essentially the recipe and the instructions for a species, it is passed on to the offspring. As the environment changes, success often requires a solution more permanent than an adaptation within an individual. The success of the species may depend upon the solution being embedded in the entire population, a true genetic shift. So for each of these, I'll give a biological example and a human example. And you're encouraged to do the same for the life's principles that your team was assigned, but either one is appropriate. So if you can just find a biological one or just identify a human one, that's fine as well. So let's look at a biological example of evolve to survive. So all of life has undergone evolution. Bacteria are an example of a rapidly evolving kingdom, particularly due to their short generation spans. The presence of uber bacteria is a result of misusing antibiotics. This has allowed the strongest bacteria to survive and pass on their survival secrets to the next generation over time, resulting in an antibiotic-resistant bacteria. This evolution means that medicines which would have originally killed off bacteria are no longer effective. And a human design example is a democracy. Democracies are constantly evolving systems representing the collective desires of the people through voting. Different information is embedded in the culture, which allows it to adapt to the changing times. Democracy is an adaptive strategy, and it ensures success of a democracy is repeated or even written into laws, which are the code of the country. These traits and strategies are then passed on to future generations. So let's look at some of the strategies that nature uses to evolve to survive. One thing that nature does is it replicates strategies that work, and this means to repeat successful approaches. Life replicates strategies that work, genetic code that manifests itself into successful strategies, for example, increased survival, means those strategies will pass on to the next generation through the process of reproduction. Likewise, in organisms that recognize and respond to feedback, behaviors that result in success are reinforced and tried again. As they result in successful outcomes, they can be passed on genetically, learned by the organism, or passed on through imitation to offspring or other members of the same community. So a biological example we get here from the crow. So many corvid species like the crow and raven are very adept at learning to use tools to access food. Individuals that succeed teach their young, and other members of the same flock are known to imitate what they witness. Eventually, these strategies become embedded in the genetic code, and learning does not need to occur. It becomes instinctual. And a human example is the bicycle. So I've shown here the first bicycle ever invented, along with the current road bike. So the first bicycle, a transport via two wheels, was invented in 1817. Since that time, the basic elements of the bike have remained. There's two wheels, there's a pedal to rotate the wheels, a seat, and a handlebar. While specific elements have evolved and improved, the basic strategies work well, and they are repeated in the modern bicycle of today. Another strategy that nature uses to evolve to survive is to integrate the unexpected. And this means to incorporate mistakes in ways that lead to new forms and functions. Recombination of genetic material sometimes results in miscoding of DNA. Often these genetic mistakes do not support life or result in significant detrimental effects, but sometimes the mistake results in a viable offspring that has an altered genetic code. The expression of this new code could be a seemingly small change, like a difference in hair color, for example. But with all of the variables and changes in a system, any new trait can turn out to be an advantage. These mistakes, called mutations, are one source for creativity, innovation, and diversity found in nature. Genetic mutations are alterations in the DNA that result in altered characteristics. Mutations add more variety to the gene pool. This diversity of traits is important when the Earth's conditions change, so what was a bad idea could likely be the key to surviving in a new environment. So for a biological example, we'll look at the elephant, the largest land mammal on the planet. It owes its size to a mutation in its genetic code over a millennium ago. What had been a smooth skin was mistakenly coded for a wrinkled skin. As a result, the surface area of the elephant increased exponentially, which led to greater heat dissipation. More heat loss, coupled with the big ears, where the elephant also loses its heat, meant the elephant could increase in size without overheating internally. A human example is our often used Post-it notes. 3M, the manufacturer of glues and other chemicals, created an experimental glue that did not quite set up as intended. This lab mistake created a chemical that had a different property than conventional glue. And rather than toss out the results, the scientists recognized the properties could prove quite useful in reusable adhesion, and the Post-it note was born by integrating this unexpected design. Today, it represents a significant share of the 3M's business. One of the Biomimicry 2IC students who are currently undergoing that program is trying to solve the challenge, how does nature innovate? And they're trying to discover new ways to solve problems and integrate the unexpected. So another strategy that nature uses to evolve to survive is to reshuffle information. And that means to exchange and alter information to create new options. So genetically, reshuffling information is the purposeful exchange of information through meiosis. When male and female cells come together, the genes are mixed. It occurs during reproduction and in cross-pollination in plants. The result is a recombination of information from two different sources and guarantees variety. Reshuffling information provides an opportunity for something new to occur. New characteristics are not always beneficial or wanted, but they do increase the number of available options. This enlarged pool of alternatives may hold a solution when conditions change and the old solutions no longer work. So for a biological example, we can look at apples. They're impressive at reshuffling information. A few apple varieties that we eat today are all clones of the original tree that bore the fruit we know and love. This is because every seed from an apple tree can be wildly different from the parent. In their native range, apple trees come in all shapes and sizes, from small bushes to towering trees of over 60 foot tall. Their fruit can be small like a cherry or as large as a grapefruit with a thick, tough skin. Their success is through this wild recombination, which allows them to survive in the world and even in cultivation. A human example of reshuffling information is when employees change jobs. Ideas and information are exchanged between companies. Reshuffling information in this way is effective enough that companies often insist on non-compete agreements with their employees when they leave for another company, for fear that the blended information will give their competitor an unfair advantage. Moving individuals into varying positions and keeping information and new ideas coming can achieve this benefit within an organization. So the last life principle I wanted to present today was use life-friendly chemistry. It's using chemistry that supports life's processes. Biochemistry, the process of assembling molecules to achieve certain functions, is the backbone of life, essential to everything from digestion, communication, color creation, and even thought. The chemistry of life is almost always occurs in or near an organism's own body. As such, it must not harm the chemist. While life does create toxins, these are produced selectively, locally, on demand, and only in quantities needed. This limitation helps ensure that when assessed holistically, chemistry as practiced by life creates conditions conducive to life. So as a biological example, we can look to the blue mussel. A bivalve attaches to the intertidal zone with a glue that cures underwater. The glue seals in a non-living bisol thread to the rock, providing the stability necessary to access the nutrients in the water column. The shell of the mussel is extremely resilient and imparts a deep blue color. Each of these functions, adherence, flexible support, structure, and color, is achieved chemically without causing harm to the mussel. In mimicking that attaching design, Columbia Forest Products Pure Bond wood adhesive eliminates formaldehyde-based glues in plywood and other sheet goods by mimicking the blue mussel's underwater adhesion. This life-friendly chemistry does not off-gas and is waterproof, achieving the necessary function of adhesion without the use of toxic compounds. So strategies that nature uses to have life-friendly chemistry include breaking down products into benign constituents. And the definition for this is to use chemistry in which decomposition results in no harmful byproducts. Nature's chemistry is not exclusively benign. Toxins produced for specific purposes are synthesized selectively, locally, on demand, and in only the quantities needed. Unlike many toxins of our chemistry, once these toxins have been released into the environment, they serve their function. The chemical product breaks down into benign, reusable substances. This biodegradability means there is no bioaccumulation of toxins, thereby limiting their effect to the targeted recipient. So a biological example, we'll look at the rattlesnake. Snake venom is particularly deadly for any unfortunate prey bitten by the snake. The toxin, when injected, is harmful for cells, coagulates blood, and the effect is the neurological system of the animal. The immobilized prey is then consumed, the venom inside causing no harm to the snake, and the digestion of the prey leaves no trace of the toxins in the snake's fetuses. Additionally, predators of venomous snakes seem to be able to break down the toxins, avoiding any deleterious effects. For a human example, Prairies is a company that developed a biodegradable fire extinguisher formula that contains no toxic glycol ethers or fluorosurfactants as conventional fire extinguishing foams do. The new formula contains biodegradable non-ionic, ionic, and amphoteric surfactants. Contrary to bromated flame retardants, or BFR, so common in human designs that every human on the planet tests positive for BFRs in their bloodstream, Pyrocool is not a bioaccumulating molecule. So another strategy that nature uses for life-friendly chemistry is to do chemistry in water. Use water as a solvent. Water is the cheapest, safest, and most non-toxic solvent for chemical reactions. A solvent is a liquid that contains dissolved substances known as solutes. A mixture of a solvent and a solute is called a solution. Water is a good solvent because it bonds easily with any molecule that has an electrical charge. It does not matter if the substance has a full charge, such as an ion, or a partial charge, such as a polar molecule. Life does this primarily through the use of membranes that are polar on the outside and nonpolar on the inside. The polar exterior allows them to mix well with water, while the nonpolar interior provides a safe haven for nonpolar parts of complex compounds such as proteins and enzymes. So a biological example is your own teeth. In your lifetime, you grow 2 sets of extremely hard, durable, and enamel-coated teeth using water-based chemistry. The durable enamel coating far exceeds the property of human-made coatings like polyurethane and is produced in our own body using the universal solvent, water. Cleaning automotive parts, here's an example of how we've moved from one system to another. So a company called Safety Clean provides a parts cleaning service to vehicle repair shops. It's usually a chemical solvent containing hazardous constituents, and even though the company will pick up, recycle, and return the clean solvent to your business, it's still a risk to the mechanics who use the chemical and to the environment. As an alternative, many vehicle repair shops found that using soap and hot water works just as well. These automatic parts washers use water as a solvent and provide the user with the additional advantage of having the parts cleaned automatically. So not only are they not exposed to hazardous products, the mechanics can be doing other tasks while the parts are being cleaned. These washers come in all sizes and it can accommodate a whole engine block. An oil water separator removes the oils before the water is recycled back into the machine. And the final strategy that nature uses for life-friendly chemistry is to build selectively with a small set of elements. And this means to assemble relatively few elements in elegant ways. Nature's chemical reagents are more complex with a limited range of reactivity, allowing them to do their job efficiently and effectively in relatively small quantities. They make do with locally available materials, usually made up of a relatively small subset of elements from the periodic table. So just because all those elements are in the periodic table doesn't mean we need to use them all. So nature uses basically carbon, hydrogen, nitrogen, oxygen, phosphorus, calcium, magnesium, iron, copper, and zinc. These elements give rise to the incredible diversity of life forms, structures, and material properties. Elements such as mercury or lead are seldom found in nature's chemistry labs, although these elements are used all too frequently in industrial products and processes. So for a biological example, we'll look at a plant leaf. It performs a wide array of functions, including energy harvest from the sun, protection from overheating, protection from herbivory, protection from sunburn, structure wind resistance, CO2 harvesting, water balancing, and more. Yet the elements found in a leaf are carbon, hydrogen, oxygen, nitrogen, phosphorus, potassium, calcium, sulfur, magnesium, silicon, and in trace amounts, less than 0.02% total, we have boron, chlorine, magnesium, iron, zinc, copper, molybdenum, nickel, selenium, and sodium. So as a human example, I'll just refer back to the Novomer developing enzymes that mimic the enzymes in plants to make plastics that we reviewed at the beginning of the class. So that gives you an overview of two of Life's Principles' main life principles and strategies, and an example of what your team can submit next month. I can't wait to see what you find. So I wanted to speak now about the biomimicry in-person session. Nestle has sent out the registration form, and I wanted to just go over a little bit of the logistics and ask if anyone had any questions. So this photograph here is the photograph of the group site that we have reserved. It theoretically holds 20 people, but I felt like if that many people come, it would be a rather crowded site. So what I will do, these campsites over here where the blue arrow is pointing along this loop one of the campsites are the most desirable campsites in the campground, and you cannot reserve them ahead of time. I'll be arriving at the Great Sand Dunes a day ahead of the workshop, and I will reserve 3 or 4 of these campsites depending on how many people come, and we can self-select to move to those. The reason these are so desirable is they have a really good view of sand dunes. They're right on the edge. They offer a lot of privacy and just beautiful sites. So I think Nestle has sent out the information about the in-person session, and I wondered how many people, by raising your hands, are thinking about coming to the session. And Mila, you want to count how many people raise their hands so we can get a straw vote?
Sure,
and then,
I'll do that.
All right, and then these registration forms will be due to Nestle by August 3rd, and we'll use those to do our planning for food and for logistics. And we will also try to connect people with other people for carpooling to go down to the site as well.
Okay, so I think we've got about 10 so far that are on. I know there's quite a few folks that aren't that are on vacation and not on the call today. But yep.
Well, that sounds great. I'm really looking forward to it. Like I said, we will be diving deeper, and you'll get the goal, the intent of the in-person session is that at the end of the session, you will have a really good straw idea of what your solution or solutions are. And so on the morning of the final day, you will be presenting those solutions to our group and to members of the Park Service who are in attendance. And it'll be a good way to meet your team members in person and just have a wonderful time.
Marie, would you just mind repeating the dates again?
Okay. The dates is the workshop starts on the afternoon of September 11th. So the morning of the 11th is a travel day. The workshop will start at 1 o'clock. On the 11th, from 1 to 2, we will be doing just a general place your stuff here kind of setup where everybody can join together and select their camping location. Then at 2 o'clock on the 11th, we will be going up to the Resource Management Office. They've offered their room as a classroom, and Jason Gearhart will be giving a PowerPoint presentation overview of water systems. Then the next day, on the 12th, we'll be working all day with the 2 experts. On the 13th will be a day when we will do some exercises and have a lot of time for team interaction based on the information that you learned. And then on the morning of the 14th, which is Friday morning, we'll be doing the presentations of what we've discovered so far, and then we have to vacate the group campsite by 1 o'clock. And then you'll be able to drive home on Friday afternoon. Okay. Well, the last thing I wanted to do was just to go through the homework assignments. So we have the life's principles. Each team has been assigned one of the major principles, and these can be sent to me by August 15th. The next webinar is August 16th, so the only point to send these slides on the 15th so that we can collect them all together and have them in one PowerPoint. You'll need to select someone on your team to go over those, and we highly encourage you, if you are the presenter, to call in so that we can hear you really clearly. The Challenge to Biology summaries, which is the summaries that you'll be putting together. Each team was asked to use the Challenge to Biology worksheet and to put them in that format. And it's critical that you send those summaries to me by 2 o'clock in the afternoon, Mountain Standard Time, on August 3rd, so that I could forward them to the National Park Service biologist and to the 2 instructors, so they can get a heads up as to where you are and what progress you've made to date. That will allow them some time to pull together additional biology that they know either from working in the park, working in this ecosystem, or from their expert, their area of expertise. In addition to the life's principles and the Challenge to Biology, I encourage you to continue working on your research. Nestle will be here until August 17th. That's her last day. So she's a great resource to get that information. And to the Eyesight this month is to look for life's principles in action and find the ways nature is performing a function that you have chosen. I've also put 2 optional tasks, a radio show that you could listen to. It's just further information about biomimicry. It may be very general for you at this point since you are so educated in biomimicry. And also, I highly recommend the optional article, The Places to Intervene in the System by Donnell Meadows. Okay, are there any questions or comments on anything I've covered today? I'll open up the floor for questions, comments, and then we'll end this webinar.
Well, I think that's it, Marie.
Okay. For the last session in August, you'll just be given one short assignment, which would be to identify some specific areas for the ecosystem that we'll be visiting in the Great Sand Dunes. And to next webinar, I'll be going into some overview on how to evaluate your projects, which you'll be doing after the September workshop, and some information about how to communicate biomimicry to other disciplines. So thanks so much. And again, if you have some questions about abstracting or about any part of the biomimicry methodology, please send me an email and continue to work with Nestle. She gave me a review of the research to date. It looks like everybody's really diving in and finding out some really good examples. And in your Challenge to Biology summary, don't forget to document eyesight observations, because actually observing nature is one really good way to discover strategies of how nature performs your function. So thanks again to Mila for hosting the webinar, and I will say farewell.
All right, thanks, Marie. Thank you, everybody. See you next month.
Bye.
Bye-bye.